Okay, so shall we start?
Yes.
Yeah. So I'm going to give a very brief introduction about Hadoop today, and before that, I'm going to introduce you to the big data, technologies which are persistent in the industry these days. So we'll be covering the first topic of the developer training today, that is the need for Hadoop.
Okay.
So the first topic here is introduction to big data. Basically, what is meant by big data for any person who's new to this term or to these Hadoop related technologies and the Hadoop ecosystem would not be able to make out what big data is. So we have our first topic, which is an introduction to big data. Big data, which the word big indicates, is very huge amount of data. It's very huge in volume, in its velocity with which it enters the system in which it has to be processed. So big data is basically the first idea that you should have in your mind by big data is very vast amount of data. Now I would like to give you an idea of how big this big data actually is. So according to the stats, we have these information that in the last 2 years we have developed or we have generated, we have produced 90% of the existing data in this world. It was only the 10% which was existing before the last 2 years, and in these recent 2 years it has grown to such a huge volume. So this is the pace with which the big data is actually evolving. It is coming into the scene. Another list of stats that I would want to share. Okay, I'll share a presentation I had delivered in one of the management systems. Okay, so here we have it's big data facts. So here it's an all-inclusive term which is used to describe vast amounts of information. And this collection of data is so large that we have our traditional database management systems. They actually fail to manage this data, to work upon this data, and to process this data. So here we have the facts. Now we are creating about 2.5 quintillion bytes of data every day, and that is a very huge figure. And 90% of the data, as I told you, has been created in the last 2 years alone. So these are some of the big data facts which make us aware of how big the big data actually is.
Okay.
We have another 2 facts about the big data industry and the amount of traffic flowing over the internet, which is 281 petabytes, 661 exabytes. It has reached to 667 exabytes by 2013. So now I hope you have got an idea of what big data is. Have I been able to make it clear to you?
Yes.
Okay. So the point is, from where is actually the big data coming? I mean, we are generating so many petabytes and exabytes of data. So what is the source behind this big data? So it's like coming from everywhere, you can say. We are using internet. We have people who are more and more number of people are becoming internet aware, and they're connecting to internet in order to solve whatever purpose is there. So everything, every transaction that occurs on the internet, everything that we do which involves a transaction or an exchange of information generates data. And when we sum up all these sources, we have this big data being built. But we have to, categorize it in some way. So we categorize it into three varieties, which is social data, machine data, and transactional data.
Mhm.
By social data, we mean every one of us uses Facebook, Orkut, Twitter. So all this data where we are posting something, where we're sharing something, we have our videos shared, any kind of sharing or transfer of information, and some more people then commenting on it, or so here we have a lot of transaction of data, and this is social data. This is the first category, which is social data. Then the second one is machine data. By machine data we mean, apart from the internet, we also have many machines which are configured to work, and they deliver a lot of information. They result in the form of data. For example, we have our sensor machines, or we have machines which are detecting the weather or climatic conditions. So all these machines are also producing some amount of data, which is a kind of information to us, and we have to process this in order to achieve what results we require. So that constitutes the second category, which is the machine data. The third one is the transactional data. That is when we are transferring some money online, or we are purchasing something. So these kinds of transactions where we have our accounts built into some firm, some organization, some bank, and we are creating some event or task which requires that organization to process some data about our account. That is a transactional data generation process. So this constitutes the third category, which is the transactional data. So this is a broad view of what all categories we can divide the big data into, and at the same time it is somewhere dividing the source of big data as well. Am I right?
Yes.
Okay. So now, till now we have got to know that we have the big data is a very, very vast amount of information, and what are the sources of big data. Now this is how we can actually visualize big data. That is the three V's of big data. That is volume, velocity, and variety. So we have already grasped that volume, it's massively huge, like terabytes, petabytes, and it is ever growing. We can well imagine that if it has grown to such huge amount in just the last 2 years, and it is ever growing, and it is evolving, so at what pace it would actually be growing in the near future as well. The other thing is velocity. See, when we are talking about social data or transactional data, this data is coming at a very, very fast pace, and not just at a very fast pace. This big data needs to be processed at that fast pace itself, because and in many systems like machine data, it needs to get results from our system in order to perform the next task. So this process of getting the big data, processing it, and then delivering the results back. That has to be very fast, and because the speed with which the big data is being generated is very fast. So this is another very important characteristic of big data. Along with volume, we should have in our mind this another feature, that is velocity as well. Because big data is not just being generated in huge amounts and it is being stored in some database or in our servers. It definitely needs to be processed in order to make some meaningful information out of it. So the second feature, which is velocity, is a very, very important part of it. And the third one is variety. We have either used or we have heard of the traditional database systems. One of them is the SQL server that we use. So these are used to process structured data. That means we have a row of data coming. We know that the data, whatever be the source, that would be in this particular format. It would have this values for these fields, and we enter those values and we constitute a row for the table. So that is what we mean by structured data. But in case of big data, it is not just structured, it can be unstructured as well. So by unstructured, I mean it can be in the form of a document, it can be a random log file, it can be a row-based data as well, it can be any form of data, whether it be structured or it be unstructured. So big data is not like it has to be in this particular format. It can be any form of data. So this brings us to the 3 V's of big data. By big data, one always have this in mind that it is a very, very huge amount of data. But you always would have to associate the other 2 V's with the volume V as well. Okay, that makes sense?
Yep.
Okay. Okay. So this is the first topic that we have covered, that is introduction to big data. Now we move to the second topic, which is the problem with existing traditional systems.
Okay.
So the existing traditional systems, what do we mean by the existing traditional systems? A very, very good example of it is the MySQL server. You've used MySQL server?
Yes.
Okay. So the MySQL server and the similar database management systems that we have been using, it's like the Hadoop and the big data technologies is into the scene since just the last few years. And before that, it was these traditional systems that were very well managing the data across the globe. As of yet, also they are quite capable of doing so, but the use case is restricted. So, yeah. So, what is the problem with the existing traditional system? That we had to include big data into our technology span. We need to process this big data in order to generate some information out of it. We need to store big data in order to process it later to generate some information out of it. And this is not possible with the existing traditional system. That is because the existing system is capable of managing, processing, storing structured data only. It is not about the volume, it is not about the velocity, but the main concern is the structure of the data. When we are talking about the existing traditional systems, they need the data to be in a particular format in order to store or process or do anything over it. But in case of big data, when we came across this form of data, we encountered that the existing traditional systems cannot store any form of data. They need to have a predefined structure. For example, tables in MySQL server, we need to define what fields it would have, how would be the columns, what would be the data type, everything before we can store any data into it or before we can fire any queries onto the stored data. So this is not the case with big data. We cannot specify or we cannot decide what kind of a structure the data that's being generated from our websites or from our Google search engine or any other particular search engine or the transactions that we perform over the net. Anything that we do would be. The structure is not defined. And this is the biggest problem with the existing traditional system. So unless you cannot store it somewhere, yeah?
No, go ahead.
Okay. So unless we can store any data, we cannot process it and we cannot query that data or generate any meaningful information out of it. So this is the problem with the existing traditional system. And another problem is to some extent also the volume of the data, because when it comes to petabytes of data, so the pace at which our existing traditional systems would process this data and deliver the results of the queries, it is not going to scale to the speed that we need to generate results on this big data. As I had talked about the machine data, where we have our machines, they are producing some data and they need some feedback as well from the data that they had generated in order to produce further results. So in that case, we need a very fast processing. A very fast processing has to be involved in order to provide it back the results with that equivalent speed. So that speed cannot be achieved with the existing traditional systems, because when the size of the data grows, the speed would definitely decrease in case of existing traditional systems, because most of them are a single machine server that is running, or they can handle the huge amount of data, but the pace here is important. So as we had discussed the 3 V's, so here the velocity would not be satisfied. The velocity V would not be satisfied. The volume may be satisfied, but then at the same time we need the velocity, which cannot be achieved. So that makes sense?
Yes.
Okay. So we have covered what is big data. We have understood what was the problem with the existing traditional system. It cannot process unstructured data. It cannot process data with that speed which is required. And it can store volumes of data, but maybe when it comes to petabytes or exabytes of data, it would in some way fail. So this was the problem with the existing traditional system. And seeing this, there was a very big requirement of having a new approach that could solve this problem, that could address the issue of having these 3 V's satisfied and producing excellent results. So seeing this, the new branch of technology, that is the big data technologies, have come up, and they are fulfilling these 3 V's in an excellent way. And we are at this point of time, we have big data being handled, being processed, being stored very, very efficiently. So what do we make out from this, that what should we have in our new approach? What should it have been the target when it was being built to have in our new approach? What should it have been included? So it was, the very first thing was that it should be able to manage a very, very large set of data. Secondly, it should be able to process the data at a very, very fast pace. And thirdly, it should not be restricted to some particular format of data or data which is structured in some way. Am I right?
Yes.
Okay. So these were the basic requirements of the new approach, and these have been very well handled by making the system distributed. The main core solution to it was developing a distributed system. So what do I mean by a distributed system? We can basically say it's a cluster. It's a cluster of many computers working together to achieve a particular task. We can say that a distributed system is where we are dividing our task into all the systems that are constituting the cluster, the distributed system, and each of them is performing its own task individually, independently, and bringing back the results, combining them, and delivering the result. So this was the main approach behind fulfilling of all these requirements.
Okay.
Okay. So now we have our fourth point and the last point for the first topic, which is comparing SQL databases and NoSQL databases. NoSQL, which brings us to Hadoop. So firstly, let's just brief of the SQL databases. I would like to share something.
Okay.
One second. Okay. So this is the SQL characteristics. We are aware of this. So let's just quickly go through it. SQL characteristics, as we know, they store data in columns and tables. We have our data in a particular format. We know every entry of the data that would be received would be in this format, and we store it in that particular format in our tables. We have relationships represented by data. All the data that we store is related to each other. We can relate it through the use of primary keys. Practically, we use primary keys or we use foreign keys. All that we have in SQL. We have the data manipulation language, that is the DML, which allows us to manipulate our data by using select, insert, update, and similar queries. we have a data definition language which allows us to define the structure, which we can do in case of data which is not in the category of big data, because the definition part is missing in big data. That is the biggest feature of big data. So it's unstructured, and here when we are talking about SQL databases, they are dealing with very well defined data. So that is the DDL, which is helping us out to define that format. Then we have transactions, where we are dealing with the process in which we are some way when we are processing the data which we have stored, and or it could be just a simple insert operation where we are adding some more data into our storage. So that is any transaction that we have with the database is what is meant by this point, which is transaction. And the last one is the abstraction from the physical layer. So what is this physical layer abstraction? It's about something being hidden, where applications are specifying what, but they are not specifying how. Like when we are storing data into an SQL table, we are specifying what is the table going to be like, what are the entries going to be like, and the data types and all the information that is required to create a table. At the time of inserting also, we are specifying the data, but we are never bothered about how it's being done at the back end. So that is what we are talking about. That is the physical layer abstraction. Then the query optimization engine. That is when we are firing queries, we are not bothered about how many transactions it is going to produce at the back end. So that is the query optimization engine, which itself optimizes the way in which it is going to perform that query or run that query over the existing data. Okay. So I think enough of the SQL.
Yes.
Yeah, one thing I would like to just cover up is the transactions in the SQL databases, which are possessing the ACID properties. This I'm going to just give a look over, because we are going to talk about this when we'll be talking about the NoSQL databases. So we have atomic, consistent, isolated, and durable transactions in case of SQL. By atomic, we mean the task that would be initiated would be completed, or it would be rolled back. Consistency is when we are performing any task, it would transform it from one consistent state to another consistent state. The data would not be left in an inconsistent state after the transaction. Isolated is when we are performing a particular transaction, like for example, we are running a query or we are inserting the database. So when it is being done, the data that would be visible to all of its users would be the one which was before the transaction. Once the transaction has committed, only then the results would be reflected. And the last one is durability. It has to survive failures when the transaction is being processed. So these are the well-known ACID properties of the SQL databases.
Okay.
So any queries as of now?
No.
Okay. Okay. So this was a brief overview of the SQL databases. We were just trying to run our eyes through over it. So now our topic is comparing of the SQL databases and NoSQL databases. That is, we are mostly interested in Hadoop. So the SQL database part is covered. Now, how is NoSQL database different from this SQL database? So let's get back to the presentation. So NoSQL is not only SQL. It's not just possessing the properties of SQL databases, but it has that extra thing which is required, that extra feature which is required to process big data. It is very efficiently addressing these points: non-relational, distributed, open source, and horizontal scalable. If we need to understand NoSQL databases, we need to have these 4 points in mind with absolute clarity. The first one is non-relational. We have the relational database management systems, that is RDBMS, and this is a non-relational database that we are talking about. Why do we need a non-relational database management system? The answer to this question is very, very clear if we have understood the 3 V's of big data. One of the V was volume and another one was variety. And we can relate this non-relational feature with these 2 V's. So when we have unstructured huge amount of data, building a relational database management system where we have relations between the data that is coming into our system is not going to solve the purpose. We have any form of data from n number of sources which is not related to, maybe it is related in some way to some other part of the data, incoming data, maybe it is not. So this feature is a very important feature where it has to be non-relational. The database has to be non-relational. It has to store unstructured data, so it does not have to depend on a particular form of table or these number of columns or any kind of a structure. It has to just be capable of being stored a huge amount of data. So this is the first point, that is non-relational. The second one is distributed. We were talking about distributed when we were thinking about the requirements of the new approach, right?
Yes.
Okay. So this is coming back. Distributed is, as we had talked about, where we can process our task on n number of systems, and we have our task accomplished on all those systems in
Cluster.
in a particular partitioned way, and we are combining all our results into one, which is making the system grow faster and work at a parallel in a parallel environment, which is delivering that pace, that speed which we require for processing big data. So that is the distributed feature. The third one is open source. The Apache Hadoop is also an open source project. So the next generation databases need to be, as we had talked, about the distributed feature. So they need to be open source because they need to be installed over a huge number of systems, and at the same time this technology needs to be ever evolving. It needs to be developed and it needs to be worked upon always, and it cannot be a registered or a copyright of some particular organization, because this is a use case in the IT industry which cannot be addressed to a particular problem, which is not addressed to a particular situation. We have big data, maybe there are many sources of big data which have not yet been recognized. So when n number of users are going to use it under n number of requirements, under n number of circumstances, they might encounter some or the other new problem or a new solution to an existing problem. So it needs to be open source, so that it can be ever evolving. It can always be improved from one level to the other level. So this is the third feature of open source, that the next generation databases, that is the NoSQL databases, should possess. And the last one is horizontal scalability. By horizontal scalability, we mean that the data which is being either stored or temporarily stored for a particular transaction has to be scaled over a huge number of systems. As we had seen that the size of big data is ranging from petabytes to exabytes. So this amount of data cannot be stored in a particular system or on a particular server. If it can be stored, processing it would be very, very difficult and very inefficient as well. So we need to store it over huge number of servers, each of which would be storing a part of it, and it would be responsible for that particular part of data and all the transactions related to that data. So that is what we mean basically by horizontal scalability. So this is a very broad view of what the NoSQL databases should address, and this is very much what Hadoop addresses. It is non-relational, it is distributed, it is open source, and it is horizontally scalable. So when we'll be into using Hadoop, we would be more realizing this feature, and when we'll be diving deeper into the concepts of Hadoop, how it works, we would be more easily able to understand how these all features it is addressing. So for now, this can be assumed that it is actually very well addressing all these four features. So another point that I would like to emphasize here is this. This would make whatever we have discussed more clear.
Yes.
So what we have some more characteristics that applies is schema free. By schema, as we know, it is a particular form of a particular structure which we define to tell the database that my data would be in this format. So since it is big data which is unstructured as well, so Hadoop is schema free. It does not require to have the data coming in a particular format, and it does not need to have a particular schema defined. Okay. Then easy replication support. Now, one thing that strikes us is that, okay, fine, we have a distributed or horizontally scalable system. We have a huge amount of data, and we are storing some part of data over every system. So what if one of the system fails, or it, because of some reason, it shuts down, or any reason because of which that data which is stored on that system has lost? That would lead to inconsistency in our data, isn't it?
Yeah.
So in order to overcome this, we have this replication support. By replication, I mean that if we have 10 files and we are copying one file over each system, and we have 10 cluster systems in our cluster, so it would not be like we would be having that file on just one system. We would be replicating that file over some more systems. If we have decided to set, for example, the replication to 3, each file would be stored at 3 different servers, so that if one of them fails, we would be able to recover this data from some other node, from other system in the cluster. So that this is what we mean by replication support, and which is very, very essential for maintaining the consistency of that data and the durability of that data. Then another one is simple API. This is very obvious in case of SQL databases. We have a very easy and a defined way of querying that data. We have queries, we have select, insert, update, alter, and n number of statements through which we can process the data which is there in the SQL database. But what about when we are talking about the NoSQL databases? So definitely when we are storing the data, we need to process it. Otherwise, there is no point of storing, and we need to recover that data in the form of some meaningful information. So that requires an interaction with that data, and that interaction requires an API. So when we are using that API, we can with ease process the data and produce whatever results we need to produce from that data which is stored in our NoSQL database. So that is what we mean by the simple API. And I had addressed this before, that we are talking about the ACID properties, because we need to take up this issue when we'll be talking about the NoSQL databases. So here it comes. The eventually consistent or base is another characteristics that should apply to NoSQL databases. We cannot say that the big data technologies which are coming up, that is the NoSQL databases, would be possessing the ACID properties. We cannot say that, because they have their own reasons that they would be processing very, very huge amount of data. So having these properties, that is the ACID properties, is a bit more of an expectation. We'll get into details of this. Yeah. So here it is. This is the opposite of ACID. And in order to make it understandable, it has been made the opposite of ACID, that is basically available, soft state, and eventually consistent. Availability, that is the basically available part we were talking about just now when I was telling you about the replication factor, the replication property, that when we were copying our data onto multiple systems in order to make sure that the data is available in case one of the data nodes fails. So that is what I'm talking about when I'm talking about basically available. Another one is soft state, which means it can be processed, it can be manipulated in a very easy way. It need not be in a state where it needs to be, like for example, being converted into some particular form and then or being put into some particular another system like a database or something and then being processed. So that is what is soft state. And eventually consistent. That is, we cannot make sure that every transaction that we are performing, it would lead to a consistent state. By consistent, I mean it would be leading us to a particular, like here the consistent is what atomic is in case of acid. As we had discussed about the atomic property.
Yes.
So here by consistent we mean actually atomic.
Okay.
So that is also here it is being specified clearly that it is eventually. It is not always that it has to be consistent, but it eventually would be, because we can very well understand that if a particular process is processing some take for example petabytes of data, so we cannot ensure consistency in that case. And we cannot make it mandatory for the database system to be consistent in that state. So it is at particular events of time, in particular cases it is consistent, but when it comes to such use cases, it might not be consistent, and that is very valid and acceptable in case of NoSQL databases. So that's the characteristics. The next point is characteristics. We have weak consistency. Availability is the first thing that we need to have, and that is addressed. Best effort, approximate answers, that is okay, because again it's when it's involving a very huge volume, it is possible to have approximate answers, and the approximate answers that would be delivered from processing that amount of data would be in themselves very accurate. Like if we are processing 10 files in SQL server, and if we are processing 1,00,000 files in the NoSQL server, so even if the results here after processing 1,00,000 files are approximate according to that system, then still they would be in any case better than the results produced by processing those 10 files, right? And the next 2 points are aggressive, that is optimistic, and simpler and faster. So this was how they are different from the ACID properties of the SQL databases, and they possess the base properties.
Okay.
Okay. So yeah. So this has made clear that A NoSQL database management system is a distributed system. And a distributed system, why it has to be distributed, this is also clear.
Yes.
So a distributed system should have, this is a theorem by Brewers. It's a Brewers cap theorem, which tells us that it can support only two of the following characteristics. That is consistency, availability, or partition tolerance. Now, why are we going through this Brewers cap theorem? That's because when we'll be talking about Hadoop, when we'll be learning more about Hadoop, we need to keep it in mind that it is a distributed system and it possesses these properties. But at the same time, it would be possessing only two of these properties. See, just now when we were talking about, we were on the previous slide, when we were talking about eventually consistent. So big data management systems are working very well, but we have made certain compromises in order to achieve that level of performance. Because we cannot expect everything that a SQL database gives us. A SQL database gives us ACID transaction properties. A SQL database gives us, it requires data in a particular format. It makes those transactions complete. So, but here there is a very big difference in that data which is being given as input to the system. And in all spheres of those three V's that we had covered. So we have to make some compromises, and this is in some way addressing that particular compromise that we are talking about. It can be just two of the following characteristics. So we'll quickly see what these characteristics mean. Consistency, we have already seen that all the nodes, since it's a distributed system, we have multiple nodes. By node, I mean every system in the particular distributed system that we are talking about, every particular system would be called a node. Okay. So all the nodes would see the same data at the same time. That is what we mean by consistency, which is more like the atomic that we're talking about in the ACID transaction properties. The next is availability. The node failures will not prevent the people the users or the process who is operating on that database. If we have 10 systems and one of them fails, it would not be like the entire system would be down or the operation that was being performed on the system would stop. It would not be this way. The system would be highly available and every operation would be terminated with proper results, the desired results being given to the user. So it would be highly available, it would be consistent. Just a second. And it will be partition tolerance. That is, the system would continue to operate despite of any message loss. If any of the components is unavailable, still the system which is performing a particular operation will complete and it would deliver the result. So these are the three characteristics of a distributed system, out of which two can be addressed at a particular point of time. So Okay. Yeah. So this is what we have covered, and it's a brief summary of what we are more interested in, that is the NoSQL characteristics. So have you been able to get an idea of some way how SQL and NoSQL databases differ?
Yes.
Okay, that is very, very good. So this is a brief of the NoSQL characteristics. That is, it is going to process large data volumes. It is going to be scalable, and there is going to be replication and distribution in that particular system. That is, it is going to possess thousands of machines. It would be potentially distributed around the world. Then the queries that we'll be running over the NoSQL database would need to return answers very quickly. Most queries would involve very less number of updates. That is because we need them to be fast. We want them to be fast, and we want them to return the results at a very fast pace. So the updates would be less, and like it is very obvious because we have the big data. It is being stored in some way. So our main task would not be to update this data, because it is some form of unstructured data. In most cases it is unstructured, in some cases it can be structured. So we have got nothing to do by updating this data. We just need to extract what we want to extract, that is the meaningful information out of this data. So it is not going to involve in any way more number of updates. It is going to just be queries and the results of the queries. Then it would involve asynchronous inserts and updates. It would be involving insertions and updates, but which should be asynchronous. That is, they should not be occurring at the same time when the data is being inserted and it is at the same time being updated. In any case, we have seen we are going to have a very few updates, but this has to be maintained. Then a very, very obvious one, and we have talked about it a huge number of times in this session, is schema-less. It is going to process unstructured data, so it cannot have a schema, a defined schema in which it has to work. Asset transaction properties are not needed. Base is fine. We cannot expect the system to have those asset transaction properties. Neither are they needed. Having base properties would work just fine. The CAP theorem that we saw, which would have 2 out of those 3 properties, and open source development, which we had addressed why the open source development is required. So this is the core of NoSQL databases, which should have these properties. And just a small brief before we end up with this session is that Hadoop is very well addressing all these characteristics, and that is why it is the buzzword in the big data industry today. And when we'll dive deeper into the details of learning about Hadoop, how it works and what it actually is, things would be very, very clear, and each of these characteristics would be very clear to you. Okay. So any queries? or
I have a
any
question.
doubts? Yeah.
The question is, what is the best case scenario where I can use the Apache Hadoop instead of the relational database or the traditional system database?
Okay.
And why? And another thing is, if I have all the things like if I have a large amount of data set, I need faster processing time. I have the cluster with the end nodes, and I also have all the ability. But what should be the basic requirement of using the Apache Hadoop, and in which cases I cannot use the Apache Hadoop?
Okay. See, the first thing is that you're telling you have huge amount of data. So
Yeah.
when huge amount of data comes in, the traditional databases are a secondary option at the very first place. Now, if you have that big data and you need to just store it and process it some time later, maybe not requiring some real-time results from it, maybe then you can use some NoSQL SQL database as well. But when you need to process it at a very fast pace, not just for the sake of processing, but to produce result at that pace, then you cannot go for NoSQL database, because it cannot deliver that result with that pace with which you would need it to be delivered.
So it's not faster. The NoSQL database. So the NoSQL database is not that much faster, or I cannot use in real-time systems. No,
it's like you can use it, but at the same time, when you have to process a very huge amount of data and at a very fast pace, that is the use case when we need to have the big data technologies in. That is the Hadoop in.
Okay.
So, as I told you, we are using the distributed systems. So the main point behind this would be that we would be running parallel processes on all those systems, and we would be executing our tasks parallelly and generating the results. So these things can be achieved with high efficiency using Hadoop. So that is the use case, like when you have a large amount of data and when you need to produce real-time results and you need to interact with very huge amount of data, process it and produce results. In that case, you need Hadoop.
Okay. So my question is, what is the basic conditions and the basic situations where we can use Apache Hadoop and where we cannot use Apache Hadoop? Even though I have like, you understand my question?
Yeah. I very well understood. So it's when you cannot use. Let me address that first. When you cannot use Hadoop is not more of a valid question. When you should not use Hadoop is the answer is to when you should not use Hadoop. It is that when you have a very small amount of data.
No. That's not my question. Is again, I will clarify more clearly. Let's take an example. I have like big amount of data. Also, with I need the real-time results. I also have the cluster with the end machines. But there are the certain conditions where Apache Hadoop won't fit in all the conditions, right? Or it will fulfill in all the conditions, regardless of any environment, regardless of any development skills. That's what my question is.
Okay.
Hello.
Yeah. So, well, then in that case, when you have all these, you have the big data, you need the results at a fast pace, then this is the ideal case for using Apache Hadoop. So, there is no reason as such that you should not be using Hadoop then in that case. Yeah, that could be the case when but yeah, as you said that you have n nodes as well, and so you have all the basic requirements for Hadoop, and you have the need for Hadoop as well because you have big data. So in that case, there is no such reason that you should not be using Hadoop, because Hadoop is meant for being used in these scenarios. In these scenarios, when we have these conditions, we were not able to deal with these conditions efficiently using traditional systems. So this is what Hadoop is built for.
So it doesn't matter. It doesn't matter what kind of hardware we have, or what kind of environment we have, or what kind of platform we are working on, or does that matter for Apache Hadoop?
Okay, so the environment is definitely it is supporting the most available and the most used operating systems, and so that can be a restriction if it is somewhere out of the way. The hardware that we have is somewhere out of the way, but for example, Windows, or we have a Linux, or Mac OS, all these operating systems are supported by Hadoop, and it is very well functional on these.
I know. Okay. Okay.
So does that satisfy your query?
Not exactly, but I understand. Like what do you want? What do you mean by it?
Okay. Okay. See, the basic thing is that when we have the three things that you are telling, big data and space and n nodes. So when we have that, and Hadoop is actually, it is still evolving.
Let's put it this way: what is the drawback of using the Hadoop, and what is the benefit of using the Hadoop in the ideal condition?
Okay, so the drawback of using Hadoop is that you need to, first thing, you need to have the knowledge of, you need to be trained in using Hadoop. The very first thing is, like, Hadoop runs MapReduce jobs.
Yeah.
So when you have to perform a particular task using Hadoop, you need to be well, known to those particular the usage of those the MapReduce algorithm.
Yeah. I got it.
Yeah, so you need to be efficient at that. You should not be. You should be aware at that. It's not like using SQL databases where you can just use those custom queries of select, insert, and all that. So that is one case that you should be very well acquainted with the knowledge of writing MapReduce jobs in order to use Hadoop. Okay.
Okay.
And other than that, one thing is there that you need to have suitable and sufficient hardware for running Hadoop. If we are talking about like big data and it is meant for big data, so you need to have hardware scalable for that volume of data. So that is one thing. Other than that, in fact, the first thing that I was talking about, that is the MapReduce algorithms, it is true to some extent, but then at the same time, in order to solve this problem, we have come up with the Hadoop ecosystem, which involves HBase, Hive, your Mahout, Scoop. So with the use of all these and with all these integrated into Apache Hadoop, that issue has been solved to a very great extent, because all these tools will help you in working over the data, the big data that you have stored in the Hadoop distributed file system, without even knowing how to write MapReduce jobs. It is not that you, when you're using these systems, you have to write the MapReduce jobs. They would automatically, they have inbuilt algorithms and jobs which would do the needful. So in those cases,
so my question is, if they have the inbuilt algorithm, the MapReduce algorithm, and if I want to use, but it didn't matches my requirement based on which I want to use. So is that possible? We can change that algorithm, or we can write our own algorithm instead of their algorithm?
Yeah, definitely. Definitely, you can do that.
And if we write it down, we should have to write it down like what exactly we need to do. Like
so,
we have to write.
Yeah, I understood your question. If your requirement is not being fulfilled by the existing solutions, you can definitely go for creating your own, and that you can do using the API that has been provided.
Provided by Apache Hadoop or provided by MapReduce?
No, it has been provided by Hadoop.
Okay.
So you can use that to write your MapReduce algorithms. There will be simple Java programs, which would be defining your mappers and your reducers, what tasks they would be performing. It's quite similar to, just in order to explain, I'm telling you this example that, for example, we have threads and we have the run method in a thread. So we have to basically implement that run method. So in case of mappers and reducers also, we have the map and reduce methods, and we have to basically implement these methods. The rest of the part about running these mappers and reducers would be handled by Hadoop. We just need to define what task we need to fulfill.
Okay.
So that can be.
That makes me more clear. Yeah.
Okay, that's great.
Yeah. So yeah, that's all from my side.
Okay. So that's all from my side as well for this session today.
Okay. Okay, so now I will talk to you, Vamsi, again.
Yeah, thanks for attending the demo, Anand.
Oh, okay. You are here.
We will contact back to you.
Oh, okay. Yeah,
okay,
sure.
Thank you, JT. Bye bye.
Thank you.
Thanks.
Thank you.